Section 3.1.2 talks about Laplace's equation in one dimension, in 1D. So if we go look back at the Laplace's equation that we found in the previous video, or in the previous unit, which is this equation over here, the right here, we have only one dimension. That means that we don't have the y, we don't have the z. Therefore, our equation becomes simply this equation right here. Now, this one can be solved. If you think about this, it's not even a partial equation in differential anymore because there's only one. There is only one single dimension. Therefore, we can even rewrite it in a simpler way. Oops, sorry, d. Now it's the same thing, and therefore we can then calculate it. And therefore, if we do the d over dx times dv over dx is equal to 0, then we integrate both sides. Integration of the left side will simply get rid of this part over here. Although when we become 0, we become like 1. We'll just get rid of it. So we can just run like this. And on this side, on the right side instead, it will get a constant. Then I'm going to write as m. You will see why. So then we have dv over dx is equals to m. Because if you remember, if we derive another times, the m, if we derive in terms of x, the m becomes 0. So it's proven so far. And so if we integrate one more time in terms of x, then we're going to get, on the left side, we're going to get v is equals to m x plus another constant we're going to call q. Or as the book calls it, actually, b. So as you can see, this simple work gave us that our potential in one dimension is this body that we have right here. But let's try to graph it now. So we're going to put v on the y-axis, of course, and x on the x-axis. So we know that when x is equals to 0, then v is equals to b. So we're going to put this point right here is going to be equals to b. And then when we can say that when x is equals to a certain number, so I just say 1 to make it easier. Actually, let's make it 2. So we can b v is equals to 2 plus 2m plus b. So let's just say that this point 2m is right here. So when we connect these 2 points, we obtain a straight line, which is what we were expecting given this initial equation. Because as you can see, it's an ordinary equation with the exponent of 1, therefore it's going to be a straight line. Now, one other thing you can notice is that this line has no local maximum or minimum. It goes down on the right or up on the left. Because, as it makes sense, as we get farther from the point in consideration, so let's say point 0, our electric potential decreases. Now, we can notice also that if we take one random point in the middle, and we take 2 other points, actually let me write this as our point right here, d of x, so let me call this point x. And then I'm going to choose other 2 points on the side. So 1 point over here, 1 point over here. They are the same distance. So this distance is going to be called A. This distance is going to be called A. It means that this point that we have on the left right here is going to be equals to V times x minus A, because we go back. And the point on this side here is going to be V equals x plus A. But as you can see, it's the average of these 2 points. The average of these 2 points is going to be equal to v of x. So the average is going to be equal to 1/2 the sum of the 2 points. So vx minus a plus v of x plus a. And this is how we prove that we have the average. As you can see, this equation works very well in one dimension, And as you will see in the next videos, it works very well in 2 and 3 dimension as well.